This is MEC 310, Environmentally Sustainable Manufacturing. This is the waste stream map, and this is a waste stream map of an injection molding process. So start with acquiring raw materials, which in this case is plastic pellets, which produces emissions from transportation and produces waste from, packaging, as in plastic bags and cardboard boxes. And then it's material prep, which consumes plastic pellets, colorants, and additives, and produces emissions from the machinery used, as in dryers to dry it and mixers to mix. And waste from this are contaminated or off-spec pellets. Next is melting and injection, which feeds plastic pellets into a hopper, which are then melted into molten plastic and then injected into a mold. This process consumes plastic pellets and produces CO2 from injection molding and waste, and produces purging waste and leftover materials in the hopper. And next is the molding process, which is what it sounds like. Molten plastic is injected into a mold cavity. This produces mold release. This contains mold release agent and energy. It produces emissions from the machinery used, which is injection machine, and waste as in defective parts, sprues, and runners. Next would be cooling, which is cooling the part until it's solid enough to be injected. This consumes cooling water and energy, and water, if not recirculated, is considered both an emission and a waste. Next is trimming and finishing, which is trimming the parts to meet specifications. And this consumes trimming tools and energy and produce emissions from the machineries used, such as trimming tools, CNC machines, polishing machines, and produces waste such as trimmings and defective parts. Next is quality control, which is ensuring that parts meet quality standards, and this consumes energy, testing equipment, and materials, and produces emissions from the energy used. And waste from this are rejected parts or testing waste. Next is packaging, which is packaging the products, and this consumes cardboard boxes, plastic bags, and pallets, and produces CO2 from the packaging machinery. And waste are packaging waste, as in using excess plastics. And next is shipping, which is shipping the products to customers, which consumes pallets, shipping materials, and produces CO2 from transportation, and packaging waste, as in shrink wrap. And some metrics that I chose for this are waste to product ratio, which is the amount of waste to products made, percentage of waste reused, percentage of waste turned into value, as in like using this waste or regrinding up the waste and bring it back to the process, or shipping or selling the waste to suppliers, stuff along those lines. And then energy consumed per unit of production. The next is waste separation, which is the amount of waste separated for easy recycling, which is kind of what it sounds like. And next is total waste production, which is the amount in weight produced at a time, or in a time. And then next, to fix all these problems or possible or waste, I guess, is the future state. And this is for raw materials, that is like using bulk containers that can be reused, so that you don't have to, so that produces, less packaging waste. And even if it does produce packaging waste, then you could use packaging waste or materials that are recyclable or biodegradable. And to reduce emissions, you could optimize your supply chains to reduce emissions from transportation. For material prep, it's using precise dosing equipment to minimize additives, utilize heating, utilize wasted heat to utilize waste heat recovery systems for dryers, so that you don't have to waste as much energy to use and start dryers. And then collect and recycle any contaminated or off-spec pellets, which means like reselling contaminated off-spec pellets back to suppliers. Next is melting and injection, which you can reduce consumables by optimizing machine settings to minimize energy and material waste. and you can reduce emissions by recovering the heat and using it elsewhere. And you could reduce waste by using purging compounds that can be used to minimize, that we can reuse and minimizing waste. For molding, it's using mold release agent that can be reused, so you don't have to buy as much, and you get more out of one, I guess. And then for emissions, it's optimizing energy usage to use only the required amount, basically using only the amount required, so you don't produce excess heat. And then for waste, it's recycling defective parts and excess materials. For cooling, it's optimizing cooling times and methods, and ensuring that wastewater is treated and reused, and implementing water recirculation to reuse water. For trimmings and finishes, it's redesigning trimming processes and tools to minimize waste, optimizing energy usage to reduce CO2, and recycling trimmings and defective parts. And for quality control, it's reusing testing equipment and materials when possible, and improving quality to be more efficient. Basically, just make the product, improve the quality of the product, so you don't have to. There's less waste. And then next would be to recover and reuse testing waste. Next would be packaging, which is using minimum packaging to reduce waste, using packaging materials that are easy to recycle, and implementing reusable packaging solutions. And for shipping, it's using reusable packaging material, optimizing shipping routes to reduce CO2 emissions, and ensuring all packaging material are recyclable. And so if you see this purple line right here, this represents plastic waste, and the plastic waste is then brought up, and as you can see it says reground into smaller pieces and brought back into the process, which would be here where it would be mixed back into with the rest of the plastics to be further used. And this orange line represents heat. This is heat produced by the injection machines that can be brought back up here and used in the dryers to basically use the heat. Yeah. Right. That's everything. Thank you for watching.